Chapter 8, Systems of Equations, Section 8.1, Linear Systems of Equations in Two Variables. We now enter the last unit of the course and change our focus from dealing with functions to dealing with systems of equations and matrices, the material being included in both chapters 8 and 9. So we begin with linear systems of equations in two variables, which is probably a topic you have some familiarity with, possibly from high school or some other algebra course you might have taken. A set of equations with common variables is called a system of equations. So we're talking about usually two or more variables, two or more equations, and kind of treating it like a set. If each equation is written in the variables x and y, then a solution of the system is an ordered pair u comma v. U and v would be numbers that satisfy all equations in the system. So a solution of a system of equations is an ordered pair that satisfies all of the equations in the system. If each equation in the system is linear, then the set of equations is called a linear system of equations. Recall that a linear equation in the variables x and y is an equation that can be written in the form ax plus by equals c, where a, b, and c are constants and a and b are not both 0. So for example, an equation like 2x plus 3y equals 4 would be a linear equation in two variables. We have x and y to the first power. We don't see x times y or anything of that sort. Example 1 shows a typical linear system, 2x plus 3y equals 3, paired with 3x minus 4y equals 13. So given this linear system, is 1, negative 3 a solution of the system? Is 3, negative 1 a solution? Well, to check this, we merely substitute the x and the y coordinates of the proposed solution into each equation of the system and see whether the equation is satisfied or not. So let's begin with the point 1, negative 3. So letting x be 1 and y be negative 3, this would give us, for the first equation, 2 times 1 plus 3 times negative 3. And basically the question is, do we get 3 on the left-hand side as we have on the right-hand side? And then simplifying, we end up with 2 minus 9 equals 3. Okay, obviously that's false. We have negative 7 on the left and 3 on the right. Let me just write one more step here. Negative 7 on the left, 3 on the right. Obviously a false statement. So 1, negative 3 does not satisfy the first equation, so it doesn't really matter whether it satisfies the second equation or not. There's no need even to check here. This ordered pair could not possibly be a solution of the system, since a solution has to satisfy all of the equations in the system. So the answer here is definitely a no. 1, negative 3 is not a solution of the system. What about 3, negative 1? Well, we'll check this ordered pair in the same way. If we substitute into the first equation x equals 3, y equals negative 1, we obtain 2 times 3 plus 3 times negative 1 equals 3. And that's a question mark at this point, since we don't know if that's true or not. The left-hand side would give us 6 minus 3 equals 3. And now we can clearly see that that checks out. So 3, negative 1 is a solution of the first equation, but it has to be a solution of the second equation as well to be a solution of the system. So we have to check the second equation also. The second equation is 3x minus 4y equals 13. If we substitute 3 for x, we have 3 times 3 and negative 1 for y, minus 4 times negative 1, and then we're asking, do we get 13 in this case? The right-hand side of the second equation is 13. Well, the left-hand side here is going to be 9, and then it's going to be plus 4 equals 13. That's a true statement. So the ordered pair satisfies the second equation as well. So since it satisfies both equations in the system, 3, negative 1 is indeed a solution of the system. It helps very much to have a geometrical understanding of the solution of a system of equations. So geometrically, a solution of a system of equations in two variables is a point of intersection of the graphs of the equations. This is due to the fact that any solution of the system has to be a solution of every equation in the system, which means it has to simultaneously lie on the graphs of those equations, which means it has to be a point where the graphs are intersecting. So solutions of systems of equations in two variables correspond to points of intersection of the graphs of those equations. Since the graph of a linear equation in two variables is a straight line, there are 3 possible scenarios for solutions of a linear system: one solution, no solution, or infinitely many solutions. If a system has at least one solution, it's called consistent. If the system has no solution, it's called inconsistent. And a system with infinitely many solutions is called dependent. Now, a system with infinitely many solutions would also be consistent because a consistent system has at least one solution. But if it has infinitely many solutions, it's also referred to as a dependent system. For an inconsistent linear system, the lines are parallel. For a dependent system, the lines coincide. Notice in the one solution case, you have 2 straight lines that intersect at just one point. So this is the most common scenario, where you have a consistent system and independent equations, meaning the equations yield 2 different graphs that intersect at one point. The point of intersection is the solution of the system. The second possibility is you have 2 lines. Again, both of these equations have to be linear equations, so their graphs have to be straight lines that never intersect. That is, the lines are parallel. So if the lines are parallel, you're dealing with an inconsistent system, a system that has no solution. The third possibility, one that you might not consider, but that is indeed possible, is that you have 2 perhaps different equations whose graphs are identical. That is, the equations actually produce the same graph, meaning the equations are algebraically equivalent, even though they might not look alike at first glance. In that case, the 2 lines coincide at every point, and essentially you can treat every point on the line as a point of intersection. Hence, there are infinitely many points of intersection, so infinitely many solutions. In this case, the system is consistent because it has at least one solution, but we also refer to the system as dependent because the 2 equations are dependent on each other. They're not independent. Their graphs are identical. Their solution sets are identical. The equations would be basically algebraically equivalent. Now, while it's helpful to understand the geometrical interpretation, sorry about that, let me try that again. Although it's helpful to understand the geometrical interpretation of a system of equations, a linear system, to solve a system by graphing is not really the most efficient approach. So although we could attempt to solve linear systems in 2 variables by graphing each equation, it's easier to use a purely algebraic method. That way we don't have to rely on our ability to graph the lines accurately to be able to determine the point of intersection or points of intersection if there are any. So if we use an algebraic method, it's more efficient. Two such methods are the substitution method and the addition or elimination method. Addition and elimination are just two different descriptions for the same method. The substitution method is best used if it's easy to solve one of the equations for x or for y, or perhaps if one of the equations is already solved for x or for y. If we look at example 2 part A, we have a system that is where the substitution method is suitable because the first equation is solved for x. X equals 3y minus 1. The idea of the substitution method is, as the name suggests, to do a substitution, that is, to substitute and express one variable in terms of the other variable. So what we would do here, since the first equation tells us that x is equal to 3y minus 1, if I replace x in the second equation, in the other equation, with 3y minus 1, and write 2 times 3y minus 1 minus 3y equals 7, then that eliminates x from the second equation and gives us a linear equation in one variable that we can easily solve for y. So let's do just that. If we remove the parentheses by the distributive property, it's 6y minus 2 minus 3y equals 7. 6y minus 3y is 3y, so 3y minus 2 equals 7. Adding 2 to both sides, 3y equals 9. Dividing both sides by 3, y equals 3. So we have the y-coordinate of our solution, but we still need the x-coordinate. Well, all we have to do now is just go back up to our first equation and just substitute 3 for y in that equation, and that will give us the x-coordinate of our solution. So x would be 3y minus 1. That means in this case 3 times 3 minus 1. So that's 9 minus 1, which gives us 8. So there is just one solution of our system of equations. In this case, that would be the ordered pair 8, 3. Usually when we write our solutions, we want to express them as ordered pairs. So this would be, if we graph the system, a pair of lines that intersect, and they would intersect at the point 8, 3. So this is a system with one solution. It would be classified as a consistent system. A consistent system with independent equations. Well, we're not quite to 15 minutes, but we're getting close, and I don't probably have enough time to do part B. So let me just continue with that at the beginning of the next video.